Hello, everyone. We're right on time, so that's good to know. Today I'm just doing a presentation on a project that we're doing at the research team at Aikido, which was to utilize LLMs to be able to identify certain vulnerabilities that hadn't been reported yet. So very quickly, just to get started, I think probably most people will be aware of this, but just to get everyone on the same page, when it comes to your applications, around about 85% of them come from the open source packages that we use. It's an arbitrary number, of course it could be more or less, but a significant amount of all the code, everything that makes your application run, comes from the open source ecosystem. And the open source ecosystem can be very, very difficult to secure, and the way that we're relying on it at the moment has a whole bunch of flaws within it. So if we just take a standard application, we obviously have a whole bunch of open source dependencies that we know about, or hopefully we know about them because we put them in there. The equation gets a little bit more complex when we add in something called transitive dependencies or downstream dependencies, which are the dependencies of the dependencies. And then we also keep going down there. We can go for about 30 layers. So it's even really just difficult to even know what your project is dependent on. This gets further complicated when we add in these kind of third-party tools that we use, maybe something like Okta for authentication, because these also have open source dependencies. So it's very hard to get a map of what we look like. Now, this looks manageable right now. It looks like I can understand this. I have the first layer of dependencies and then the next, and that's dependent on this. A more accurate representation would be more like this, because everything's convoluted, everything's dependent on each other, and everything moves around, and it's very difficult. So if one of these dependencies was to be turned malicious or have a significant vulnerability in it, let's just call this little red dot here log4j. If that was to happen, then it can have this crazy upstream effect, creating everything, making everything malicious, and ultimately turning your application vulnerable to something that maybe you weren't even aware was there. And how we kind of solve this, or our best bet of solving this at the moment, comes from public disclosures of vulnerabilities in open source projects. So for example, if we take one, this here was from a tool called UA Parser. UA Parser, the maintainer's NPM account was taken over by a malicious actor. They installed credential stealers and crypto miners in it. And we know that we would be vulnerable to this because there is something called a CVE report, which is what this is. And I know that this version of UA Parser has this malware inside it. And because of that, I know that if I'm not using that version, I'm relatively safe. So this is an example of a malicious, when something malicious like this has happened. But it's not always malicious behind this. So if we have another one here, this is called Dirty Pipe. This was a vulnerability for local privilege escalation inside the Linux kernel. And again, we rely on this in the same way. There's a CVE number. It's defined with certain versions. I know if I'm relying on that version of the Linux kernel, then I'm vulnerable to this vulnerability. And then here we have probably the most famous example, which is log4j, which we all know what happened there, but remote code execution available. Again, this one wasn't malicious. It was just a vulnerability that was discovered through Minecraft, of all places, but yeah, you never know. And what's kind of crazy about this one is that this happened in 2021, in December 2021. That was a terrible month for anyone in AppSec. But 2 years later, there was a study done that showed that 30% of the applications using log4j were still running a vulnerable version, which is kind of crazy. But this is essentially how we do it. And there's a really big flaw in how this all works, is that it requires all of the vulnerabilities to be disclosed. And if they're not disclosed, then we don't know they exist and we can't protect ourselves against it. So for example, vulnerabilities are found usually by one of two people. The maintainers themselves will find a vulnerability, or a security researcher will find a vulnerability. Of course, users can find them and report them as well, but that's typically how it's found. That goes through a process and a CVE number is created, and they're published in a series of databases like the NVD, the National Vulnerability Database, so that we know that that CVE relates to this tool. We then usually have a tool called SCA, Software Composition Analysis. It looks inside our application, maybe it creates something like an SBON, and it checks to say, hey, are we using any of these vulnerable components that are in these databases. That's how it works at the moment. But as I said, what if these were never disclosed? And they often aren't disclosed. And they're not disclosed for a number of reasons. Often a maintainer will discover a vulnerability themselves. They will patch it, but they won't report it. I have a lot of sympathy for some of the reasons of why this can happen. If you're maintaining an open source tool on your weekends and it becomes popular, and you don't want to have to fill out a series of forms to disclose a vulnerability that you've already fixed, then I can understand that. However, that's not how security works anymore. We are completely reliant on everyone disclosing these vulnerabilities. So it creates a big error or a big flaw for us. The other reason why this often can happen is because people will intentionally not want to disclose vulnerabilities. They don't want to kind of show that they've got a critical vulnerability in their application, so they don't do it. And there's a name for this. Officially, it's called silent patching. I'm trying to rebrand it to shadow patching because I think it sounds cooler, and then more attention gets onto it. But we'll see. We'll see if it catches on. But shadow patching is essentially I'm going to fix a security vulnerability in my open source project, and I'm not going to tell anyone. And that's typically why it happens. Again, a lot of reasons for this: reputation concerns. Maybe you generally don't have time. Potentially, there's a backlog in some of these databases and getting accessed. So maybe there's a few months between you fixing a problem and it actually becoming available to the rest of the world. But none of these are kind of good reasons. And because we're so reliant on this, and you can see with a series of events like the XZ Utilis event, like Log4j, like how vulnerable the entire internet is to all of these. So we created Intel, which is it's an open source research project that we do. Everything we publish publicly. We have a GitHub database. And essentially, this was born out of a hypothesis that we made is how can we, as quickly and as easily as possible, find unreported vulnerabilities? It's a very difficult thing to do, but we had an idea that if we could train LLMs to read the change logs of open source packages, we would be able to identify when a security fix was made and correlate that to see if there is a related CVE to it. So we built Intel. We also have a nice graphic version of it. If you don't like GitHub and you like pretty things, we have that there. And it started off, we thought it was going to be very simple. We'll train a change log to read through these. We'll train an LLM to read through these change logs, and we'll go off. But we quickly ran into a lot of troubles, particularly at scale, because change logs are not always in the same place. A lot of the time they're in GitHub. Sometimes they're on the websites. They're never in the same format. There's no standard change log format. So we had to kind of come up with a whole bunch of solutions to identify this, particularly at large scales. And we managed to do that, and essentially the architecture that we looked at is we identified the top 5 million open source projects. We scrape all of the times, every time that a changelog or a new changelog is added, we scrape that information. We use an LLM to first put everything into a standardized format, and then we identify through that changelog with an LLM if any security vulnerabilities has been fixed within it. We then cross-check that with the CVE databases to see if there's any identification of vulnerabilities. And then finally, we have a human in the end who actually confirms the vulnerability and gives it a severity score based on a scoring process that we have. So we still need a human in there, but the human component is far less reduced because of the LLMs that we're able to do. And we found a lot. So we started this actually in January last year, in 2024. Throughout the year, we found 550 undisclosed vulnerabilities, including 61 of them which were critical. 550 may not sound like a lot, but you have to remember also that we're talking about some of the most popular open source tools that exist, and having any vulnerabilities inside them that aren't disclosed is kind of a big issue. What we also thought was that eventually we figured that most of them would be disclosed eventually. However, we found that 67% of them were never disclosed. And even quite a lot of the critical severity ones were never actually disclosed to a database, which is concerning, obviously, for a number of reasons. And this year, we've increased it. We've already found 362 so far, which is a lot more than what we kind of had found at this point last year. This is due to the models obviously being improved over time, but also a lot of critical vulnerabilities also now being found in them. And to take a look at some of the more interesting vulnerabilities of what are we actually finding and how are they. So in an open source project called Axios, it has 56 million weekly downloads. This is one of those projects that most people are kind of vulnerable to it at some point downstream. They're dependent on it. We found a high severity issue in here, and today there is still no CVE for this, even though it's been more than a year since we discovered this one here. Apache eCharts, this one's kind of interesting, not because the vulnerability, it was a cross-site scripting vulnerability that we found. We ranked it a medium because the exploit chain was a little bit difficult to go through. 1 million weekly downloads, so again, very popular, and again, no CVE has been reported for this one, so people are completely unaware if they have this vulnerability in their things. Another one here, this one was critical, past reversal vulnerability. This one is from a Lateral CMS composer, and again, very, very popular, 2 million downloads, and again, no CVE going through it. So lots and lots of interesting information that we're finding out there that people aren't aware of. We publicly public all of our results. We have an RSS feed that anyone can tap into. Everything's published on GitHub, so anyone that wants to add this into their products or add this into the research, they can do so without permission from us. But we had such success with this, we decided we wanted to create a new version of this and actually identify malware inside these packages. And this has been crazy, and we launched this year, only a few months ago, and we've already found some absolutely kind of wild things, again, using LLMs in this process. This time, same area, we scan all packages that are included in package registries, like if they're being uploaded to NPM or PyPy or Maven. We scan all of them, every single one. We scan them with traditional static analysis tools, and we then feed all of that information into our LLM, which then identifies how likely it is that these have malware and whether or not a human needs to review this as well. And some of the things that we found through this model is kind of crazy. We've found 11,000 malicious packages on NPM and PyPy at the moment. It's an absolute cesspool out there. Usually we can detect them in about 5 minutes. And if you're interested in some of the things that we found, kind of the one that we got a lot of press on was something in the XRP SDK. So XRP, or Ripple, is a cryptocurrency. It's one of the largest cryptocurrencies out there. The official SDK, which a lot of the large currency exchanges like Coinbase and Bybit were using this as a way of communicating with the Ripple ledger. We discovered that there was actually someone had put a backdoor in this, which stole private keys. It essentially meant that had this been merged into, let's say, Coinbase, that anytime anyone interacted with the Ripple ledger, it would have stolen the Coinbase customers all of their private keys, not just for their Ripple wallets, but for all of their wallets. So it would have had a pretty catastrophic impact out there. We were pretty happy about this one. We got a lot of press for it. We discovered it in about 10 minutes, and the Ripple team were responsive to us in about 45 minutes. So it was a pretty good response time to there. OS Info Checker. This is a really interesting one we found last week. This one is interesting. This is very sophisticated. This was a dependency in dependency. So this project looked a bit dodgy, but it was being hidden by being a dependent in other tools. And what we found here was it was using this eval function, which usually always is dodgy, but it was decoding something in base 64, and what it looked like it was decoding was a single character here. And we couldn't figure this out, but luckily our LLM model could for us. And what it actually was it was using Unicode characters that were hidden and not being rendered on there that were containing the malware. But it gets even weirder than this, because when we finally managed to decode this and look at what it was doing, it was calling something from another domain. That domain was wrapped in base 64. When we figured it out, it turned out to be a Google Calendar invite. The title of that Google Calendar invite was also in base 64, which went to the final version of the payload. So this one here was so well hidden, it was kind of crazy, but we still managed to pick it up. And the last one that I'll talk about before I get off the stage, this one here was from the Lazarus group. This one I just think is hilarious because we found this malicious code. We got flagged for it. We looked at it. We couldn't figure out what was malicious about it until finally we looked at the scroll bar down the bottom, and they had literally just used white spaces to move the malware off screen, which was calling a domain. And it almost worked, to be honest. So that one was really cool. When we looked into this, it was doing a whole bunch of things, stealing credentials. It had crypto miners in it, and we attributed this back to the Lazarus group based on a series of indicators. But that's what I've been doing. That's what we're doing at the research team at Aikido with Intel. We've been using LLMs to try and streamline the process of securing the open source supply chain. Everything we do is published publicly. So yeah, thanks.